Okay. Today we're going to talk about the one-step SN2 mechanism that we talked about earlier, and we're going to fill in a lot more of the details. And then on Wednesday we're going to talk about the two-step mechanism, which is the SN1 from before, and fill in again some more of those details. I've updated the Canvas site and the book. I put links to the videos for each one of those. So were there any questions about the SN2 if you looked at the book or if you looked at the video? So does that mean I can ask you questions about it? So I guess it does. So the PowerPoints for this are pretty straightforward in terms of how an SN2 reaction occurs. So this picture right here shows the idea that the nucleophile needs to attack down the carbon halogen or carbon leaving group bond. We're going to start with halogens as the leaving group, but we could expand that, and we'll expand it. So the nucleophile has to come down and attack that. And the reason why is that, remember how we had for our carbon, our sp3 hybridized carbon, how an sp3 hybrid carbon looks like this. It's got a big lobe, and then it's got this little tiny lobe that we kind of forget about until now. And so what happens is when the nucleophile comes in with its pair of electrons and its orbital, it then can overlap with that little tiny lobe to form the transition state. So there is a possibility, or was a possibility, at least theoretically, that the nucleophile could have attacked from the front side. But now that we know about this little lobe of the sp3 hybrid orbital, it has to attack from behind because it's basically going to use that orbital to overlap with the other orbital of the sp3 hybrid, of the hybridized carbon. So that's the reason why it has to be backside attack for this molecule, or for this reaction. And then once we do that, then we end up forming the trigonal bipyramidal transition state, which again we had talked about before. The idea that then if it's a negatively charged nucleophile, you're going to have some charge on it, some charge on the leaving group, but it will be trigonal bipyramidal in terms of its geometry. And so what happens is, as the nucleophile approaches the carbon, the other bonds of the carbon begin to flatten out until they become perfectly trigonal bipyramidal. Then as the leaving group leaves, they go in the opposite direction. So that these three bonds are pointed in this direction, and over here they're pointed in the opposite direction. And we know that because now we know about chiral molecules. So now I can go in and say, okay, let's make this a chiral halogen, and then look at the product and see whether or not it's the opposite enantiomer. Well, it's the opposite configuration on the carbon, whether it was the same or whether it was a 50-50 mixture of both. And so in that case, that confirms that it has to be backside attack for this. And so for some of the SN2s, it's a simple one-step reaction, just a transition state, no intermediates. I'm going to complicate that a little bit in a few minutes. by talking about different leaving groups and how we can make them leave. Okay. And so then we have our rate equation. One thing I'll point out is primaries react the fastest. Actually, a methyl halide is even more reactive than a primary. That makes methyl halides, well, it makes some methyl halides are actually very toxic. So for instance, if you have CH3 iodine, that's methyl iodine, that actually is classified as a bad chemical in the lab. And the reason it is because it can undergo SN2 reactions very easily. So if it gets into your system, if you're using it and somehow you breathe it in or somehow the liquid gets into your system, what happens is it starts to methylate all sorts of things. And we don't want to methylate like DNA and RNA and enzymes, because sometimes those mutations might give you like superpowers, but sometimes they'll kill you. So that it methylates so easily that it's not a good compound to be using in the lab, and you have to use it with a lot of with gloves and in the hood and everything. So it's the fastest, then primary and secondaries. Tertiaries don't react in an SN2 one-step mechanism because the steric hindrance around the carbon, the nucleophile cannot approach that carbon. It turns out that when you have a halogen attached to a double bond, that also does not undergo SN2. SN2 is only for sp3 hybridized carbons. So when you have a benzene ring, and I've used the circle here for benzene ring, which we'll get to probably next semester why it's a circle, but for benzene rings, it's a halogen attached to a double bond. You actually have the entire ring in the way, so the nucleophile cannot get at that carbon. But anytime you have the halogen attached to a double bond, it will not undergo SN2, only the primary, secondaries, and tertiaries. And there's some pretty good slides here in terms of what you're looking at. So if you're the nucleophile and you're going to react with a primary halide, there's enough steric room here for you to be able to attach, to be able to come in and attack the carbon with the leaving group, which is in this brown color. As I start to add more steric hindrance to methyl groups, that area for the nucleophile to overlap its orbital is getting smaller. And then by the time you get to a tertiary, or in this case, this is a very sterically hindered secondary, there's just nowhere for the nucleophile to attack from the backside. Now, what we talked about probably a month ago, was the idea that the one-step mechanism occurs fastest, and that's what this is, SN2, occurs fastest with primaries and secondaries. But the other mechanism, the multiple step mechanism, the SN1, occurs with tertiaries and secondaries because the carbocation is more stable. And so what happens with a molecule like this is that if it can't undergo SN2, it will lose the halogen and undergo SN1. So those are complementary reactions, which is why we're going to talk about them today, and we're going to talk about them on Wednesday. And then we're going to summarize them all together. Okay. And then if you have a tertiary like this, again, very difficult for the nucleophile to get at that carbon that's attached to the leaving group. So this kind of gives you that perspective in terms of how the molecules react. Now, What we want to do is we want to practice writing mechanisms. And before we do that, the final sort of piece of evidence is what happens if you take a chiral molecule, meaning one enantiomer of a molecule, and you do an SN2 reaction on it. Because some people originally questioned the idea that the nucleophile would attack from the backside, and they said, well, maybe it'll attack from the front side like that. And the experimental evidence for that is that if you take the R2-bromobutane and you react it with hydroxide, the first question you need to ask is the product optically active? Because if it is, in other words, if it rotates plane polarized light, then that means that the product contains maybe only one enantiomer, but it certainly contains a majority of one enantiomer. So the first thing they did was they tested it to see, is the product optically active? And the answer is yes. Then the question becomes, well, what happened to the chiral center? Is the chiral center retained as R, or is it inverted, and that's the term we use, as S? And we find out that it's inverted. Now, this is not a trivial experiment to do, because what you have to do is you have to use the pure R of the bromobutane to begin with. You have to isolate the product pure, because you can't have any bromide in there. And then for the product, because there's no relationship between R and S and D and L. Do you remember that from last week? Because I'm making a different molecule, its S configuration could be either D or L. Now over here, I don't know what it is. It's either D or L. That would be easy enough to measure. So the sign of the rotation isn't what I'm looking for, in so much as I'm looking at what that sign is and does it correspond to the R configuration or the S configuration of now 2-butanol. Because it could be that this R is positive and the S of this molecule is also positive. So the sign doesn't necessarily change for the rotation. But what definitely changes is the configuration goes from R to S, because the chiral center is being inverted. Because all the groups that were pointed to the left are now being pointed to the right. And so if I did this, this would be number 1, 4, 3, and 2. 4 is away from me, so going from 1 to 2 to 3 is counterclockwise. Whereas over here, it's 4, it's 1, it's 2, it's 3. So going from 1 to 2 to 3 is clockwise. So the experimental evidence is that when we do an SN2 reaction with a chiral molecule, we end up with another chiral molecule where the chiral center has been inverted. Okay. Does everybody see that? So we need to be able to write the mechanisms of these reactions. Right? And there's a summary page that kind of says, okay, here's the important things on bimolecular nucleophilic substitution, which is where the 2 comes from. It's because it's one step of 2 molecules reacting together. And so all of these on inversion of configuration, the backside attack, the trigonal bipyramidal geometry, and the kinetics being bimolecular are the important parts of that reaction. So let's write a mechanism. All right, so as far as writing a mechanism goes, let's say that I said I want to write the mechanism of hydroxide reacting with 1-bromobutane. Now, initially what I'm going to do is I'm going to tell you what the mechanism is, but by Wednesday we're going to get to the point where I'm going to expect you to be able to determine what the mechanism is. And I'll give you a little bit of insight into how you're going to do that. Primary halides can only do the one-step SN2 mechanism. Because remember, the two-step involves what kind of intermediate? It had a plus charge on the carbon. What's that called? It's called a carbocation. See, the people that wrote the book, they thought, and this is probably a good idea, well, if we introduce this a little bit at the beginning, then when we get to it a couple of weeks later, everybody will remember what they did in the past, so we can just kind of go into more depth. I think there's a flaw in their logic. They assume that stuff sticks in your head maybe a little bit longer than it may. And your job is to make it stick for the rest of the semester and year. Right. So, in order to do the other mechanism of SN1, we need a carbocation. Primary carbocations can't form. So that means primary halides have no choice but to do SN2. So when you look at this molecule, you'd say, oh, primary halide got to be SN2. Now we're going to talk about the strength of nucleophiles here. I'm going to call a negative nucleophile a strong nucleophile. And so you've got a strong nucleophile plus a primary halide. That's going to be automatically an SN2 mechanism. But for the moment, I'll tell you that. And since today's all about SN2 mechanisms, that's probably the last time I'm going to tell you, oh, this is an SN2 mechanism, because that's all we're doing today. So what happens? We have the OH electrons are donated to this carbon, and at the same time, the carbon-bromine bond breaks. So we have to show those two arrows of the OH minus attacking this CH2 and then the carbon-bromine bond breaking. That's going to put us into a trigonal bipyramidal geometry. So the trigonal bipyramidal geometry always looks like this. It's always going to have the carbon with the 3 bonds, the bold wedge, the dashed wedge in the plane, and then dashed bonds between the nucleophile and the leaving group. So in this case, the nucleophile is OH, the leaving group is Br, and then what's attached to this carbon that's attached to the Br, I've got 2 hydrogens, and then I've got basically a propyl group. And you can arrange those groups whichever way you'd like. Unless it started out chiral, at which point you have to make sure that the groups stay in the same position in order to undergo inversion on the other side. Okay. So this is my transition state. I'm missing 2 things. I'm missing the delta minus on the OH and the delta minus on the Br. because the OH is starting out negative. It will become zero formal charge. The bromine starting out zero formal charge, becoming -1. And so its charge in the transition state is the average, which is delta minus. And you can think about what's happening. What's happening is the charge is being transferred from the OH to the Br. So these are really easy mechanisms to write. One step with the transition state, and you'll always have to write this transition state. So that's how we write the transition state for an SN2 mechanism. Everybody with me? Hopefully the thermostat's set at like, 50 degrees or something. This room is extraordinarily warm. I know, it's putting everybody to sleep. 8 o'clock's putting everybody to sleep, plus this lecture's putting everybody to sleep. I got it. It's going to be a long week. Now, before we talk about some of the other variations on this, right now our leaving groups are pretty much, sadly, they're pretty much limited to halogens. But we're going to change that. What we need to talk about is we need to talk about what makes a good leaving group and what makes a good nucleophile. So let's start with the idea of what makes a good leaving group. And it turns out that there's only one factor that goes in to making a good leaving group. And that is leaving groups, the best leaving groups are the weakest bases. So there's an inverse relationship between leaving group ability and basicity. The stronger the base, the weaker it is as a leaving group. The weaker it is as a base, the stronger it is, or better it is as a leaving group. So halogens are ideal. But that doesn't mean that we can't use other groups and make them leaving groups. So I'll just kind of foreshadow ahead. One of the best leaving groups that we can have is an O attached to a SO double bond attached to a benzene ring with a methyl group on it. This is called a tosylate group. And it is by far and away there's modifications you can make to this to make it even better. But this is a really, really good leaving group. And so, why is it a good leaving group? Because this is a really weak base. My question to you is, why is this a weak base? The answer. Anybody want to give me an answer before I go to the wheel of misfortune here? And we work our way through.
Is the charges spread out? The negative charge?
Okay, the charge is spread out by...
The oxygen?
The charge on the oxygens is spread out, but how is it spread out? By...
Pulling electron density.
Yes, but how? We have two ways to pull electron density. Induction and resonance. So how is it done here? How do we spread the negative charge out over the oxygens? By doing what? By being able to write resonance structures. So we can write resonance structures which will spread out the negative charge. Okay, but what's that get me? There's multiple parts to this answer. The question was what? Why is it a weak base? And part of that answer is because it has the ability to spread out the negative charge, to delocalize the negative charge using resonance structures. What else has to go into the answer then? What does that do to the molecule? It makes it more stable. And so the more stable it is, the weaker it is as a base. Right? We go back to our fundamental principle that says if I have an acid and I make the conjugate base more stable, then the more stable this is, the more the equilibrium is shifted, which makes this a stronger acid and makes this a weaker base. Right. So tazolate is a really good leaving group because it is a really lousy base. Why? Because it's very stable because of resonance. Now, how about fluorine, chlorine, bromine, and iodine? Which one of those is the best leaving group? And since, let's see. And since we will give you some chance for some participation points, we'll make this a, let's see, we first of all should make sure I have the right class, which I don't. Now that I have the right class, let's make it a word answer. So, the letter. Just put the letter, you don't need to put the negative charge on it. Which one of these is the best leaving group? F, Cl, Br, and I. I'll give you a minute. And then be prepared to answer the follow-up question, which will be, nobody can anticipate what the follow-up answer will be. Follow-up about why. Thank you. It'll be why. So the question is what? Which one is the best? Is that what I asked? The best leaving group? Okay. I think we have 30 people. Okay, let's see what we've got. Well, we've got what I would expect. F and I. As close to a split as you can get. So that you know what that means. That means we need to take... First I need to lock down these answers. Although I didn't have to. So let me give you a minute to discuss with a neighbor what you chose, and then we'll re-vote and see if any answers got moved. Okay, time to re-vote then. Once it goes from being loud to more quiet, then a discussion's over. So go ahead and vote. Okay. We didn't really move that many people. I'm going to lock that one down. So, okay. Best leaving group is going to be the what? Weakest base. So which one of these is the weakest base? It's either F minus or I minus. Okay, you don't like that question? HF or HI, which one is the strongest acid? Strongest acid. How many people say HF? Your hand went down really quick. Yeah, but you can't be influenced by peer pressure. HI. Is HI the strongest acid? And others didn't vote? What? You voted for HF? So what kind of acid is HF? If I put it in water, is it strong or weak? If I put HF into water, is it going to completely dissociate or is it only going to partially dissociate? If you were back in general chemistry right now, HF is one of those acids that we like to do a lot of ice chart reactions with, or ice chart problems, because HF only partially dissociates, which means that it is a weak acid. HI completely dissociates, and so it is a strong acid. So given that, which one is the stronger acid? HI. Which one's the weaker base? I minus. So I minus then is the best leaving group. on the periodic table, when we go CNOF, ClBrI, in terms of acidity, going from left to right increases and going down increases in acidity. HF is stronger than OH, which is stronger than NH, which is stronger than CH. And then HF is weaker than HCl, HBr is stronger, and HI is the strongest. Okay, so we have to remember that. And if we do, then that makes I minus the best leaving group. So that's it. For leaving group ability, it's all about basicity, inversely related. Okay. So if you're a weak base, you're a great leaving group. Now, for the sake of argument, I'm going to talk a little bit about nucleophilicity here for a minute, because they go together. So nucleophilicity is just the big word of the day for the strength of being a nucleophile. Well, nucleophilicity isn't as easy because it depends on how you're going to look at the relationship. For a horizontal relationship on the periodic table, you end up with it being related to basicity and the stronger the base, the stronger the nucleophile. So when you're looking at a horizontal relationship on the periodic table, it means that it's a direct relationship. The stronger the base, the stronger the nucleophile. So what do I mean by a horizontal relationship? Well, I mean on the periodic table that I just drew, CNOF, and then your Cl, your Br, and your I, it means that if I said, okay, N minus would be stronger than O minus, would be stronger than F minus. And of course C minus, and I'm going to throw in H minus because we're going to get to that eventually. That's the order of nucleophilicity. So H minus and C minus are stronger than N, stronger than O, stronger than F. Which means that a hydroxide is stronger than an F minus. So that's the horizontal relationships. When we get to vertical relationships, it turns out that the experimental data doesn't match the strength of the base. So in other words, when we go down the periodic, we should be going up the periodic table, and F minus should be the strongest nucleophile of Cl, Br, and I if basicity was the factor, but it turns out it's exactly the opposite. So when you're in a vertical relationship, it turns out that as you go down the periodic table, nucleophilicity increases. Which means that I minus then is the strongest nucleophile of the halogens. Okay, so that's the strongest of the halogens. Now, it turns out that O minus, that any of these three beat any halogen. So an OH minus is stronger than an I minus. But for the halogens, or when you go down the periodic table, you have this relationship that is basically inverse of basicity, but it really doesn't affect, it's really not all about a basicity. Instead, it's about what's called polarizability. So when you go down the periodic table, polarizability increases. And then the question is, what's polarizability? I call polarizability squishiness. And so what do I mean by that? Well, first of all, as you go down the periodic table, what you learned in general chemistry was, as you go down the periodic table, what happens to the size of the element? It increases because you're putting more electrons around it. And that's true for a negative charge as well. So that means as you go down the periodic table, those anions get larger. And that leads to being able to be polarized. And what does that mean? Well, remember that in an SN2 reaction, what we really want to do is we want the nucleophile's orbital to overlap with this little teeny tiny sp3 orbital of the carbon. And so what I want to be able to do is to concentrate as much electron density into that orbital as possible, because the more electron density it has, the stronger the overlap is going to be. And then actually the lower the energy of the transition state. So if I can better overlap this orbital with the sp3, I'm going to get a lower transition state energy, which is going to lead to a lower activation energy and a faster reaction. Well, you have to basically have electron clouds that are movable. And the more electron clouds, or the farther away from the electron clouds get from the nucleus, the less likely the less tight they're bound. And so that leads to like a squishiness where you could like take the electron density and kind of move it, bless you, and make a more concentrated orbital. So like iodine's like a Nerf ball. You could move the electron density around. Whereas fluorine, because it's small, those outer electrons are held really tightly by the nucleus. It's more like a golf ball. It's not very squishy at all. And so the more you can concentrate the electron density, the more overlap, the better overlap you'll get, the stronger overlap, the lower the activation energy, because the lower the transition state energy. So that's how we explain the experimental result, that as you go down the periodic table, the nucleophilicity increases. So nucleophilicity isn't just basicity. It is horizontally, but it's not vertically. And then, of course, if you have diagonal relationships, then you have to think about, okay, which way am I going to form my diagonal relationship? But I will say that OH minus is always a stronger nucleophile than any of the halogens. But if I had an O minus and an S minus, which one would be the stronger nucleophile? And I put them the way they are on the periodic table. So which one would be the stronger nucleophile? S minus? Because it's more polarizable. So we need to know about nucleophile strength as well as the leaving group ability. And so those things you need to remember. Leaving group ability is based on basicity only, and nucleophilicity is based on basicity horizontally, polarizability vertically. And I'll define one last thing. In my world, strong nucleophiles have a negative charge. So if you don't have a negative charge, you're not a strong nucleophile. Now, my world is somewhat limited, and I'm eliminating a lot of the gray area here to start with. A weak nucleophile, then, is going to be neutral. It still has to have lone pairs that it can donate. So here's a couple of examples of weak nucleophiles. Water and alcohol are both examples of weak nucleophiles because they're neutral, but they still have lone pairs that they can donate from the oxygen. Okay. And these are weak nucleophiles. These are also then, they can become good leaving groups if when I need them, which is going to be next time. So what we're going to do next time is, if you did not watch the video or you did not read through the textbook on chapter 7, which is basically what we pretty much finished today, you need to do that. Chapter 7 will be the problems I put on Canvas when those problems are due. I think I had them due Friday at midnight. And then on next Monday will be chapter 8, problems. Right, but we're gonna start on Monday. No, we're gonna start on Wednesday. I told you it's gonna be a long week. We're gonna start on Wednesday with a little in-class quiz with where I'll give you some questions to work through on your device with nucleophilicity and basicity. So I'm going to ask you the basics of how does it go on the periodic table. I'm also going to ask you maybe to rank a couple in terms of which one's stronger, which one's weaker. Okay? So that will be the in-class quiz at the beginning of class on Wednesday. If you have questions, again, come see me or email me.